Welcome to my lightning research talk. I'm going to talk about detecting images generated by neural networks. So detecting fakes is really as old as image, as photography itself. People would manipulate images from the very beginning. So here's a famous photo of Lincoln that was actually a photo of Calhoun with Lincoln's head on it. Joseph Stalin, of course, was a big fan of when he would jail his comrades, he would just crop them out of his photographs. And so what has changed is really that the fakes are getting much easier to make with these advance of neural networks, things like these kind of face swapping and generating new images and things like this. They're just very, very much easier to do. And so people wanted to try to detect these neural network generated fakes, and there has been some prior work, wasn't working too well. So here is kind of a representative example. They're actually using our work from my lab, CycleGAN, so they're translating from an image of Monet to an image that looks like it was done by Van Gogh. And then, you post something on Flickr, on Twitter, oh, incredible, Monet's masterpiece was actually painted by Van Gogh 10 years earlier. Look at this. And so what they wanted to do is to say, oh, actually, no, this is real and this is fake. But the problem is that this only worked for this particular method, for this particular type of GAN. It didn't work for any other method. And so what we wanted to do is we want to see if we can get some detector to be universal, to work on all different types of deep network software. Okay, so one way to do this is you just train a classifier on all of these things, and then maybe you wait a couple of years and then you test it and see if it still works on new ones that will happen in a couple of years. Now, we didn't want to wait, so what we did is we trained on just a single one, and then we wanted to see if it would work on all the other ones. Okay. And so, of course, this is very difficult because there are lots of differences in architectures, the data sets, the objectives. But hopefully there is some commonalities that will enable us to do this. That's what we thought. And indeed, when we look at like the Fourier representations of the average images, we see that there is actually quite a big difference between the synthetic and the real Fourier spectrum. So at least on average, we know that we have the signal, but do we actually have it for any individual image? Okay. And so what we did is we took a standard GAN, popular GAN, progressive GAN, okay, we used that to generate a whole bunch of images, and also took a whole bunch of real images, and then trained a standard discriminator that could basically try to tell the images generated by this guy and the real images. Okay, and basically it kind of looks like a GAN itself, but the idea is that this thing is fixed, so it's not updated. So this is a much easier problem. Okay, and then we just tried it on all the different approaches and see how it does. And of course, on the GAN that it was trained, on the neural network that it was trained, it was perfect. It got us 100% performance. So that's great. Okay. But of course, what we're interested in is what happens on these other things that has never seen a training. And it actually turns out that it was doing pretty well on many of them, although not all. Now here we decided we are going to do a little bit of a trick, which is called data augmentation, which is basically also added various blurry versions of the data and just messed around with it a little bit. And then you can see, boom, for most of them, you're able to get almost 100% performance. Okay, and so that was very surprising to us. It was kind of we did not expect. Now, it didn't work as well for the deep fakes and the super resolution, but for that, actually, the not augmented versions were already doing pretty well. Okay, and so it was very surprising, and it was also surprising that actually the blurring at test time were still detectable. So we can actually detect very blurry images still. Okay, And we tried it on a website called whichfaceisreal.com, and our method was doing at basically 93% performance, which is better than humans. And so we thought, okay, it's great, but there is still much left to do. So CNNs are just part of the pipeline. In a deep fake, this is the neural network part. There is a whole bunch of other stuff that we're not looking at. So that's definitely something that we need to be looking at. And it's also in the real world, people use this in a different way. So we can detect which method is fake or not, but for any given image, it's very hard to kind of find the calibration. Is this image fake or real? What's the threshold? Also, for real fakers, they're going to try a whole bunch of images and just pick the best one that spool our system, right? So there is plenty of stuff to do, and the future architectures will change, and also our method is susceptible to adversarial attacks. So there is plenty to be done, but I think that this is a very exciting direction. Thank you very much.